Well, first of all, let me thank Amaury and Peter and also Anton and Etienne and all the staff at Serum for making this conference and this whole series of conference possible. It's really a great pleasure to be here today, and also a very great honor to be speaking here today. And I have to apologize, I think. Sometimes I get this advice, you shouldn't start your talk by apologizing, sorry for that. But in fact, there's a large number of people in this room who've heard this particular talk of me quite recently before. In fact, whoever went to this famous birthday conference of Allison's in March in Oxford might find some very familiar things in here. For those who really want to keep up the thrill, I place one new picture, and maybe then you can say, this picture is new. If at some point you wake up and say, this picture I didn't see. In fact, I stole this picture from a previous version of a talk that I gave in Lumini like 9 years ago. So you could say, well, no, I remember that picture too. So there's a lot of old stuff. In fact, it's part of a story that goes back to the 1940s, in fact, so maybe I'm justified to speak about old stuff. And I should say this is joint work with André Depperschmidt, who's in Freiburg, and Timo Schlüter, who's in Basel now. And it's about coalescence times of ancestral lineages in two-dimensional logistic branching random walks. And the nutshell version is the biologists have been right all the time, and now mathematicians can prove some of it. And so more specifically, I want to, discuss about the Wright-Malekow formula, which goes back to work of, I have to admit, I recently learned that it's the Wright-Malekow formula. I would usually have called it the Malekow formula because of his 1948 book. But in fact, Allison and Nick informed me that if you really properly read Wright's 1943 paper, you realize there's a series expansion in it, which if you do the series, which you didn't literally do in the paper, you find the same formula as Malekow did. But anyway, so the setting is we want to look at a population that live in a spatial habitat, and let's say it's a two-dimensional habitat, and I'll be a bit vague whether it's continuous or discrete, but Malekow's assumption certainly was it's like the two-dimensional plane, so think of continuous space, and let's say it's a space-time homogeneous situation. I mean, of course, the world isn't flat and we don't really have the full two-dimensional plane, but as an approximation, and which is, I guess, okay if you think of a large population that's spread over a large space, and locally for the individuals, it looks like the space is infinitely large, which is maybe to some extent an okay approximation. And you want to study how does genetic variation arrange itself in space. If it's been around long and it has been sort of created by mutation, then has been carried around by individuals mating and moving and getting offspring and so on. And a very basic question is the following. Let's say you pick two individuals, and because of spatial homogeneity, you could always say one of my focal individuals I pick from the origin and the other I pick from some other site, let's say X. And you ask the basic question, how likely is it that I see the same genetic type twice? Of course, there's lots of assumptions you have to make about how the genetics works and how the mutations come into play. And I'll be looking at the most simple situation where you think of mutations come according to, in the jargon, the infinite alleles model. So whenever there's mutation, there's a completely new type. And all we record is whether or not the two individuals we see have the same type or not. We don't look into the details of what the sequence information might be, which is maybe justified if you think of 1948, people wouldn't have known how to sequence anyone. And nonetheless, Gustav Malekow gave this remarkable answer, a fairly explicit formula for that. Well, it's not literally, it's not literally inequality. Here's this formula. For that probability of sampling two individuals of the same type when you sample from a certain separation, and here it is, and it involves this K0, the modified Bessel function of the second kind of order 0. Well, it's a well-known special function that solves a Bessel ODE like here, and we'll see a bit in a minute why the Bessel ODE comes naturally into that picture, with hindsight at least. And So morally, yeah, you plug in square root 2 times the mutation rate times the spatial separation divided by sort of a parameter for the standard deviation of the displacement between parent and offspring. You plug that into the Bessel function and you have to normalize it properly. And into the normalization goes, well, I mean, this term I think I find sort of digestible. I mean, this is sort of, if you think of 2 pi sigma square, like the radius or the area where you typically would put your offspring, and the delta being the density. So this is like the area or the number of offspring in your immediate neighborhood, or number of individuals in your immediate neighborhood, and then you need this extra normalization term, which I find a bit mysterious, but comes from well, sort of fudge argument. And then there's the thing that, I mean, it's known that this Bessel function has a singularity. You can't really plug in, you can't let the sampling distance be very small, because there's this logarithmic singularity that the Bessel function, that this particular Bessel function has. And of course, that's a probability. It shouldn't be infinity. It shouldn't actually be larger than 1. So you argue that, well, this approximation is okay when the sampling distance isn't too small, and you introduce some cutoff parameter. That's how I think of this. Some kappa, where you say the approximation is okay as long as you have a distance more than kappa between your samples, and let's not be precise of what happens when you're too close. And but if you're willing to say, let's assume all that, then this is what you get. And the way Maleko got this was, by looking backwards in time, which was quite remarkable, I guess, given the I guess people have been looking backwards in time all the time, but for the mathematical population genetics modeling, I think that's quite innovative. And the general idea is the following: how can it be if I sample at separation y to see the same type twice? Well, I mean, there are these 2 individuals, they have parents. None of them should have experienced a mutation relative to their parent. Otherwise, because of the assumption how the mutations work, they would have been different types. So this is 1 minus mu squared. This is sort of, I find, very digestible. No mutation. And then you say, well, let's imagine the separation changes by going back 1 normally distributed step, according to 2-dimensional, let's say, isotropic normal. And let's average out where those parents might have been. If you sort of postulate that going from a child to a parent and looking at the spatial displacement, that is like a step according to a normal law, then either you step to 2 different sides, and that gives you that integral, and then you have changed the separation by the difference of the 2 steps that you've taken. Or, and now it becomes a bit murky, it might have happened that you stepped literally to the same side, of course, which doesn't really happen if you think of 2 normal random variables, because they have a density. They wouldn't literally hit the same side. But nonetheless, let's pretend it's so, and then you get this extra term, and this 1 on delta, which accounts for the probability. Once you're actually there and there's a population density delta, then there's a chance like 1 on delta that you actually pick the same parent. This is my hand-wavy thinking about this. And it's much nicer explained in many places, in particular in Allison's lecture notes. And I advertise these, and it's very fortunate to have Allison here. So for any questions, I can deflect to her. But let this be so. So this is our starting point. This is the Maleko formula. And you can also alternatively, which by the way is also in one of Allison's papers with Nick and Franz de Paulis, look at it in the following way. Let's pretend when you go back, if you have this picture in mind of the 2 ancestral lineages where you sample 1 from the origin, 1 from X, and you go backwards in time, let's make time continuous, and let's say the spatial embeddings is like there's 2 Brownian motions. So the difference is again a Brownian motion, of course run at twice the variance. And you say, well, they're certainly not going to coalesce while they're too far away. Let's say while they're further than kappa away, they just move around like independent Brownian motions. And once they've reached that distance, of course, as Brownian motions, they cannot jump. So they really reach that distance kappa at some point. And then I say, whoa, whatever happens, it's some parameter phi of kappa. That probability if I had actually sampled at that specific distance kappa. Or let's maybe pretend that if you sample at distance kappa or less, you have some constant and call that constant phi. And then, of course, the rest is, how can it be that if you do that, if you follow that picture, that you pick the same type twice? Well, you follow these two Brownian motions until they reach the separation kappa, and none of them may hit a mutation along the way, which, well, let's pretend, I mean, had this, in discrete time, I had this factor 1 minus mu to the square, and here in continuous time, I'll put this factor e to the minus 2 mu times the tau, the collision time, or actually the time that they need to come to that distance kappa or less. And then, of course, you get the expectation of that, which is a Laplace transform of the time a Brownian motion, a two-dimensional Brownian motion starting at a point of distance x needs to reach distance kappa of the origin, to the origin. And of course, it's well known that this thing solves a certain Poisson problem. And here's the PDE that you get. Of course, you get the 1/2 Laplace, but because I'm running it at sigma, at twice the speed, because there's two Brownian motions, it's a difference. There's no 1/2 in front of the Laplace. So that's what you get, and this is, of course, also why the Bessel function comes into play, because, I mean, it's a completely symmetric problem. You can reduce everything to just a distance. It's just a radius question. And, of course, the radius of a two-dimensional Brownian motion is a Bessel process. And its generator looks like that. And you can just, you solve it and you recover the Wright-Maleko formula. That's another way of thinking of the Wright-Maleko formula. And it's quite beautiful, isn't it? On the other hand, it's also known that it's not entirely rigorous, and there are two known problems that Alison has been teaching to many people, including me. One thing is, I mean, you pretend that there's a stable, homogeneous population that's sort of stationary in space and time and has a constant, or in expectation, constant population density, say. And not only in expectation, but sort of in a sort of ergodicity type sense. When you average over a large region, you should find area times density plus small fluctuations. I guess that's sort of built into the philosophy of the thing. But it's known that there is not actually such a thing. Well, at least not of the way where you say, well, there's a density of a constant density, everybody has independently offspring, they disperse around the parent, and then it starts again. Because you can do exactly that, and of course you get branching random walks or branching Brownian motions, depending on what motion mechanism you put into, or various variants of that, which are famous models in probability theory. Very well studied and very beautiful, the rich theory. And it turns out that in dimension 2, they don't actually have an equilibrium. And that has been observed in the 1970s by Joe Felsenstein in simulations, when you looked at finite spaces, and it has this catchy, invented this catchy title, which really sticks. It's a pain in the torus to simulate these things, because, well, you simulate them and then you see a lot of empty space and a few extremely dense clutches. And whatever you do, it doesn't really fit to this idea of a more or less homogeneously spread population. And in infinite space, you can prove that of course, you can start with an infinite population. You will always have somewhere particles, but they'll typically be far apart and in high piles. And that's what happens in the infinite two-dimensional space, as, for example, maybe in the most general context proved by Olaf Kallenberg in 1977. And another problem is, it's clear what we did, and it's very plausible, I think. For a sample of size 2, you start two Brownian motions, and when they come closer to kappa, then you say, well, let's basically stop and replace everything by an effective parameter. But what do you do when you have 3 or 4 or 5? Do you then start 3 Brownian motions, and when 2 of them come together, you sort of stop the pair and replace it by some effective thing? But the problem is, the third guy, if you do that with 3 and then you restrict to a pair, it's not the same law that you would get when you start only from 2. It's not so entirely clear, and as far as I know, then nobody really found a completely consistent way of doing this literally with Brownian motions, maybe except for Peter Köpernick, but I'll come to that, but it doesn't literally work in two-dimensional infinite space. Well, anyway, of course, people did recognize this. I mean, the observation is more than 40 years now. And What you can do, and what people have done for many, many years, is instead of the continuous space, look at the discrete space. There you can meaningfully condition on constant local densities or on prescribed local densities according to some externally given function, say, and you find the family of stepping stone models, or in mathematical terms, the family of Voter models. And there, of course, you have this beautiful way of making this intuition rigorous, of going backwards in time and following the ancestral lines. And I guess most of you know there's a wonderful duality with systems of coalescing random walks, and many more or less explicit computations are possible. And it's a wonderful machine, I should say. Of course, it's a bit artificial that you say, well, let's fix the population size to be this number once and for all. And you don't have sort of a way of, the model doesn't keep track of how the population interacts with its environment and maybe regulates its own size via feedback with the environment, but no, you just decree that. Well, you can do it. You can give up this requirement of fixing the population size by putting a feedback into the system. You say, let's look at these branching random walks. I can't make them supercritical because then they would just grow beyond all bounds, locally even. And I can't make them subcritical because then they will just die out, and I don't have a stable equilibrium to talk about. But what you can do is I make them feedback super or subcritical depending on what the local density is. And I have a focal local density in mind, and I set up the model in such a way that when the density is much smaller than that, then there will be supercritical growth. And if it's much larger than that, there will be subcritical growth. And it's sort of then the thing of its own accord, if you like, will fluctuate around its prescribed equilibrium, which is in a sense realistic, but also highly complicated. And then it's no longer clear at all what the ancestral lineages are. They're not random walks, and it's hard to compute with them. Then there's this very elegant remedy of reversing the picture in a sense and inventing the spatial lambda Fleming-Biot processes, and this whole family that extends from that, which takes the continuous space really seriously and still has a very well-defined sampling mechanism, which is consistent. You can have arbitrary sample sizes, you can have arbitrary arrangement in space, how the samples are picked, and you can very precisely describe how the ancestral lineages of these, that you follow these samples, are going to evolve. They're literally going to be coupled Lévy-type processes, so they necessarily have jumps, which of course, when you look at from far away, will more or less look like Brownian motion again. And in fact, there was Raphael's talk yesterday, who didn't have the time to expand it as much as I have time, but it morally had a version of the Maléco formula, or actually an extension of it because of the inhomogeneity that is derived from the spatial lambda Fleming-Biot world, which was invented by Allison, and I guess this is the basic reference. And then, as pointed out, there's a very recent preprint by Peter Köpernick, a student in Oxford, who observed that if you're okay with compact space, and you could make the space large by saying I'm taking a very large square with a periodic or reflecting boundary conditions, then I can still have a finite mass in it, which makes sense, and I could look at variations of the classical Fleming-Biot process, which has a constant density, and so it doesn't die, but locally will still fluctuate, and so locally it will almost look like the thing that Maléco maybe had in mind. And you can describe quite precisely what the sampling formulas are, and they are of the type. You glue in Brownian motions in between the coalescence points, and they do come, we have to glue in bridges that actually do come together. So that's another way of going about the thing, which I'm not competent to talk about. And of course, the downside is you kind of literally speak about the infinite space. You can speak about the infinite space in 3 or more dimensions, but that's not going to help either. Well, anyway, so let's, what I'm going to talk about is, I'll go down the discrete world. So I'll stick to a discretized space. And one excuse for doing that, that has also been observed long ago, is that the Maléco formula, I mean, for discrete space, let's say, if you really fix the population size to be constant, so you go to the stepping stone models, you can compute this probability that Maleko was interested in very, very explicitly, of course. It's just a generating function for the collision time of a pair of random walks that you start at some distance. And it turns out that if you tweak the parameters correctly, and here in this example, I looked at a particular version of a two-dimensional, this should of course be a d equal 2 of a two-dimensional stepping stone model. And of course you have discrete distances. I mean, you can take a pair of sides and they're on the grid, so you cannot really have a continuous variable for the distance. But if you take not even particularly far away distance like 8 or 10 and compare what to the answer that you would get from the suitably adapted Maleko formula where you choose the kappa parameter, right? You get that curve, and I think, I mean, there's nothing to be desired here. I mean, the curve is, for all practical purposes, as good as the other model, isn't it? So in this sense, maybe it's justified, if you want to think of the Maleko formula, to think of discrete space, and I'm going to think of a discrete space, because the rest of the talk, I'll be focusing on an answer that works in that context of what I call the remedy B, so of looking at branching random walks with feedback on discrete space with discrete particles. And of course, there's a huge list of literature where people studied this starting in the 1990s, or maybe even well earlier, with biologists who had non-rigorous ideas in simulations, and many people here in the audience worked on variations of that thing. And in fact, I would have hoped to talk to Sarah, who also worked on a continuous time version of the model that I'll be presenting in a second. Well, hopefully next time. And so I consider a version of logistic branching random walks. And before we go into that, let me briefly observe that there's a scaling property built into the Maleko formula, which actually, if you like, comes from the type of singularity that this Bessel function has. Namely, if you say I'm going to sample at a large separation, and I introduce this parameter n here. So n is not a population size; it's really a mathematical scaling parameter that I use to pump up the distance. And I'm thinking of a small mutation rate, and let's say I'm making the mutation rate mathematically as a small power, a small negative power of the distance. So the larger you sample, and think this way, I'm sampling at a large distance in a situation where the mutation probability is small. If it so happens, you plug that into the formula, you go to the asymptotic of the Bessel function, and it turns out it's a very, very simple answer you get. 1 minus 1 on gamma, where gamma is this exponent here, or twice that exponent. So you see, you get a non-trivial answer when the separation is some negative power of the, when the mutation probability is some negative power of the separation distance. Or put differently, when the mutation probability is when the separation is large and the mutation probability is not so small, then the probability is essentially 1 that you see 2 different types. These lineages one of them will hit a mutation long before anything else happens. Okay, and now here's the model that I actually want to speak about. It's this thing here. You have discrete particles in discrete space and time, and here's my notation. Eta n is how many, by the way, how many minutes? 10? Oh. So eta n is the number of particles at a particular position in a particular time. And the game they play is that every particle will produce a Poisson number of offspring, but the mean will be a function of the local density field around it. So here's the formula. And so if there's no one else, I will have m offspring on average, and m is larger than 1. So if there's no one else, it is like a supercritical branching process. But then we subtract this weighted average of the particle numbers in some neighborhood. So the lambda here is a finite range kernel. And the idea, sort of the intuition that I would use is to say, if I'm here at x and then there's somebody else at z, then my average reproductive success is being reduced by this number lambda of that separation. It's sort of this the idea there's some type of competition. these people from over there at Z, they eat some of the resources I need to reproduce, so that reduces my chance of successful reproduction in some way, and it's encoded in this way of modifying the mean. Of course, there's thousands of other ways how you could think of putting a feedback into the system and sort of translating that into a mathematical formula. It turns out that this is quite a convenient one for our computations. And then once you create your offspring, they disperse according to, let's say, independent random walk steps. So everybody randomly takes some step. You can think of nearest neighbor if you like. Some finite range thing. And to make our computations simple, we think of a symmetric random walk. So you don't have to distinguish in your mind between going backward and forward, but you could do something more general here. And then, I mean, now we computed the average number of offspring, and they're created and they do their jump, and by the beautiful superposition properties of the Poisson, you could also equivalently describe the model as follows. You compute this mean, and then you Poissonize it every space-time point. That's the same thing. In this thing, it's sort of a variation of a probabilistic cellular automaton. And so that's the system I want to work with. And of course, if you turn off this competition parameter, if you set the lambdas all to 0, then it's really a branching random walk. Because the m is larger than 1, it's a supercritical branching random walk, so it just grows beyond all bound. And the way we set it up, there is feedback. And well, it's mathematically, it's attractive, I think, as a model to think about. It's not attractive in the sense of interacting particle systems that when you add more particles, you increase stochastically the law at a later time, exactly because of the minus here. When you add more particles, it could be that this is actually detrimental for someone who has then less offspring, and it's not a priori clear what happens. So, or put differently, I mean, for these interacting particle systems which are attractive, there's a standard theory, for example, which you can use to prove that there's equilibria and that there's convergence and so on, which isn't available here. Nonetheless, in some regime, we can do something, well, there's lots of variations that you could think of. I mean, this is one specific choice with the Poisson law and this particular choice of feedback function. And yep. And so the first result is that there's actually a stable population model to talk about. So in fact, yes, there is an equilibrium, at least when m, it should be larger than 1. For technical reasons, it should be less than 3 for our proof to work well. And the competition parameters should be small. So I'm not specifying how small. So there's two things. I mean, the lambda 0 is how much it's a competition with people at my own side. And then there is the lambda z, which is how much competition is there with people at neighboring sites. And there's two conditions here. It's essentially, that both should be small, and also the competition at neighboring sites should be small compared to the local competition. I mean, this second thing is, I would say it's more a convenience choice, which makes our computations easier. I'm reasonably confident that you could weaken it. But as it stands, generally small competition parameters are necessary. Because small competition I can tell you the truth behind it. Small competition means, because the mean is proportional to 1 over the competition parameter. Small competition means, on average, a high mean, a high stationary occupation number, and a Poisson with a high mean has a law of large numbers. So in a sense, there is stochasticity in the model, but when the competition parameter is small, the stochasticity is controlled. In fact, you could do a law of large numbers thing by rescaling the mass and taking the lambda parameters to 0. And I mean, it's a beautiful French tradition, for example, the works of Sylvie Méliard and her school, who derived then integral differential equations from this type of thinking. But I'll stick with positive small competition parameters. And so the message is there is an equilibrium, and you start from some reasonable initial condition, and you will converge to that equilibrium. And then, in principle, you have the setup to say, well, there's an equilibrium, so I can think of it as being stationary in law in space-time. And I can I mean, they're discrete particles. I mean, I didn't put it in the formulas, and it's a nightmare to put in formulas, but in principle, you can keep track of who descended from whom. You can invent a labeling scheme. I mean, take Harris-Ulam labeling or something that's well established for how people speak about branching processes. So you can keep track of who had which child and which jump did they take, which displacement did they have, and so what is the spatial embedding of the ancestral lineage. It's in principle there. And so all I need is, let's give this a letter. So this is my x. So xk is the position of the ancestor when I go back k generations for the sample that I picked from the origin, and x prime is the same when I go back k generations for the sample that I picked from site x. And let's wait until these two ancestral lineages coalesce. So they must be at the same site, but also in the same individual at the same site. And let's say tau coalesce, that's the time we take. And so here's our main result. It's of this type that are advertised in the remark about the scaling of the Malekov formula. So if you sample at a large distance and you ask the coalescence probability to be, what's the probability that it takes very, very long to coalesce? Say, and really long means a power of the sampling distance. I mean, it's sort of, again, n is a scaling parameter here, not a population size parameter. So morally sample at separation n. You could, I mean, x is any point, any space, a two-dimensional vector. You could think of a unit vector, say. And you sample at separation n, and you ask, what's the probability that it takes longer than n to the 2 gamma for this coalescence time to happen? So they have to, it takes, when you take gamma equal 100, so it takes really tremendously long. That's unlikely, but in the limit, not so unlikely. It turns out the limit is 1 on gamma. And of course, gamma needs to be larger than 1. It's clear when gamma is 1, so I'm starting at, even if you think of Brownian motions, you start 2 Brownian motions at separation n. It takes them of the order n squared to come anywhere, even in appreciable distance to each other. Or if you think of, I mean, of course they're not going to hit, but even if you think of discrete random walks that you start in 2 dimensions at separation n, they take time n squared to hit. They take a bit more actually to hit. And well, as it turns out, it could take quite long actually for them to hit. And that essentially is behind the asymptotic analog of the Malekov formula that I was advertising, namely, if you think of this situation, the mutation parameter is small. It's some negative power of the separation. And I parameterize it to be n to the minus 2 gamma. In fact, you can have a prefactor. It turns out in the scaling, the prefactor doesn't matter. Any positive prefactor will do. And the probability that when you pick the same from that separation, that you see the same type twice, which of course is the expectation of, well, 1 minus the mutation probability taken to the power twice the coalescence time. Because for each generation you back, you pick up this factor of 1 minus mu n squared, because none of the lineages is allowed to hit a mutation. It turns out that converges to 1 minus 1 on gamma, which is exactly the number we got from the scaling relation built into the Malekov formula. And in fact, this is essentially the same, these two results, and it's a, well, I made this joke before that if there should be one proof in a 45 minutes talk, here's a chance you can prove it, but I'll skip it, and it's really just a two-line argument and with a bit of the Markov inequality in it, sort of. So morally, it's also well known that sort of the asymptotics of the Laplace transform and the Taylor asymptotics of the random variable, they're sort of in a one-to-one relation. And by the way, the same thing has been observed without, as far as I know, making the connection to the right Malekov formula at the time by Erdős and Taylor, who in 1960 considered two-dimensional random walks. I mean, literally in the paper, two-dimensional simple random walk in discrete space and time. And they asked about, well, literally they asked about hitting 0, but I want to take out 0 because of the singularity. Let's say they hit a distance of 1. And they have exactly the same asymptotics. You start, let's say, at distance n. You ask how long does it take to reach distance 1? What's the probability that this takes longer than n to the 2 gamma, and it turns out the answer is essentially 1 on gamma. So it's essentially the answer you get from the Malico rescaling formula. And the way Erdős and Taylor proved it, if you go to their paper, is by explicit computations of the return probabilities and the renewal decomposition of the probability of being after n steps back at 0. When you start at 0, you decompose this according to when you start at x, you first come to 0, and then you do that after k steps, and then again for n minus k steps you come back, and so on. So there were explicit computations, and of course, I mean, certainly Erdős could do all this, presumably in his head, and why shouldn't he? But then it turns out it's actually a very simple argument behind this, namely, how can it be that the random walk takes so long, at time of the order n to the 2 gamma, to hit order 1? And the cheapest way to do this is just to say, well, I'll just go away, I'm not hitting 1, I'm going to hit a large ball. I'll exit a large ball of radius n to the gamma before returning to the origin. And the probability for this, you can, if it were Brown in motion, you could compute it explicitly because you know the harmonic function in an annulus for the 2-dimensional Brown in motion, or if you like, the harmonic function for the 2-dimensional Bessel process, it's just a log. And if you compute with the log, you just exactly get that answer. And morally, that's the nutshell proof of what we do. This argument is so simple and so robust that you can do it with things that aren't actually random walks, but that are morally random walks when you look according to a suitable renewal structure from suitably far away with a suitably coarse-grained grid, or with the wrong sort of glasses, and you see everything a bit blurred. And so here's coming back to our ancestral lineages in these population models. I mean, this slide is, I don't invite you to look very closely at it. All I want to say is, in principle, by the way we set up this Poisson number of offspring and as a function of, yeah, thank you, of as a function of the configuration, you can say, if you condition on what the population configuration is in space and time, what would the probabilities be that the ancestral lineages take this or that step in space-time? So there are, in the jargon, random walks in dynamic random environment. And their quenched law is given by this formula. And there's also a version of that when you have a pair, and you have to distinguish when they're at the same site or not. And you can also, in principle, write down what is the probability that they would coalesce in the next step as a function of this space-time configuration, which is an okay messy function that you don't want to take expectations of. At least I don't want to, if you can avoid it. So the idea really is, in a nutshell, we have to invent a regeneration construction so that when you look at these ancestral lineages, not in their real time axis, but along their regeneration construction, so you count how many regenerations have I seen, they are almost random walks. And more than that, these regeneration times, you shouldn't have to wait too long for the regeneration to happen. So there should be a suitable tail decay of the regeneration time with a certain sufficiently high power so that you have sufficiently high moments of the regeneration time. And we need that when you start them from a certain separation, then the joint law of the two things until their next joint regeneration is very similar to what you would get if you were to place one of them artificially in an independent copy of the environment. So that you could say, I pretend they're two independent objects. Because after all these computations with the Wright-Malico formula or with the Erdős-Taylor formula, they pretended that you had a random walk, which is the difference of two independent random walks. So if you can translate your scenario into that world, then you can essentially copy the computations from the masters. And that's what we did. We found a regeneration construction and observed things along regeneration times and plug this into the asymptotics. That's sort of the natural version of the proof. And of course, then the hard work and 80 pages of mathematics and stuff go into controlling that the error that you incur in each step and everything doesn't mess up the limit. And then that's sort of my nutshell message. And 2 minutes for proof ideas, excellent. One thing is that behind this, I was advertising this, behind this particle system, there is the evolution of the means. If you recall that I said that the way I think about the particle system is that you compute the mean number of particles that will be at a certain site at the next time step, and then you draw a Poisson with that mean. If you were to skip over that step and just say, let's compute the mean, and let's iterate that, compute the mean again and again and again, you have a deterministic function system, which has a very nice fixed point. It just goes to its fixed point. It's very well behaved. You start it basically whatever you like, as long as it's positive, and it goes to this fixed point. And then, because we are Poissons whose means are well behaved and large, we have a fair chance of not being too far away relative to our means. And so the idea is that you chop space-time into certain blocks, where you say, I have a block here, this is sort of at a certain time, I have a block where the particle density is well behaved, it's above this certain shape which is going to grow. Think of this green thing as what the deterministic system would be doing. It would be growing to its equilibrium everywhere. And if I have in a certain region a particle configuration which does that, then with high probability after a certain suitably tuned time lag, I will have a larger region where that happened. And whether or not that happened will only depend on the randomness that is sort of localized in these yellow blocks. And now you're in business. Now you can basically do the standard machinery. Things that occur in blocks, you tune the parameters so that with very high probability, the good thing that you require, namely this growth and spreading of the population, occurs in the block. Overlapping blocks, when they're far enough apart, have no more overlap and become independent, and then you can compare to percolation. And that's what you do. And another picture ingredient is you can start whatever configuration you have. For example, you start here from one particle and you start from another particle there. And by doing them jointly with the same copy of the Poisson offsprings, you get that they become identical after some waiting time. And that helps you to obliterate all information that you obtained on the way of whatever might have gone wrong. And this is the new picture, by the way. Whatever went wrong is the yellow here, and it will not percolate into the region where you're controlling the system. And there you regenerate. There's lots of things we can ask about, but thank you for your time, and these are the references.